In the last chapter, we saw that when X is a scheme, we have this notion of a sheaf of modules on X, and we saw various constructions for these things, kernels and co-kernels of their morphisms, tensor products, and so on. There are some problems, namely, an arbitrary such F is just too general to work with. It's hard to do any calculations. It's hard to prove any results here. And the second problem is where to get such examples. So somehow until now, we have very carefully constructed the few examples we worked with by hand, like the skyscraper sheaf, the twisting sheaves, but how to get such things more generally. And the idea generalizes something which we have already seen, namely we saw that when R is a ring, then we got this nice space, X equals spec R, a scheme, an affine scheme. And now the idea is we just take the theory of modules, so let M be an R module, then we will get from this a sheaf M tilde, which is an O spec R module. So this generalizes this construction of starting with something in commutative algebra and getting some more geometric data from it. And we will afterwards restrict to OX modules, which at least locally, which means on the cover of an arbitrary scheme by spec Rs, are of this form, and these will be the quasi-coherent sheaves from the title. And so now I present the definition, and you should think about whether this definition seems familiar to you. So this is this sheaf M tilde associated to a module. So if R is a ring and M is an R module, then we need to define what the sheaf does on any U inside spec R open. And we just define this M tilde on U as the set of collections phi, which is a collection of elements phi p of the localization of M at P, where P runs through all of these points in U. And they should satisfy that locally they're given by some fraction. So in other words, for all P in U, we find F, the denominator of the fraction. This is a function, an R. And G, which is the numerator of the fraction. And this should be now an element of M, such that we also find this open neighborhood UP of P. And on there, phi is given by G divided by F. And this is now in this localization of M at Q. This should happen, this equality here should happen for all Q in this open neighborhood. And also, of course, F shouldn't vanish there, so F is not in Q. All of these things. Okay, and if you think about this for a second, in fact, I could basically just copy paste this from somewhere earlier, namely, when we put M equals to R here in these blue parts, then we exactly recover our definition of the regular functions on the open set U of spec R. In other words, we immediately see that if we put M equals to R, then the R tilde that we get is exactly this structure sheaf, which is, of course, a module over itself. More generally, the same kind of arguments that we saw before show that this here is a sheaf, and also the M tilde on any U is an R tilde on U module, right? Because if you have this collection of phi p's, phi p is an MP, and then you want to multiply it with a section of this, and you get a collection of lambda p's, where lambda p is in the localization of R at P. But MP is an RP module, so you can just multiply them together, kind of pointwise, like this. And then these properties just hold on the nose. So somehow this thing is a module over this ring, but this ring here is also the sections O spec R of U by this first line here. And so in other words, on U, the module that we get is a module over O spec R U, and this all fits together, making M tilde an O spec R module. Okay. And this will be called the sheaf associated to this module M. And we start with proving some nice properties about it. And this is in the situation above, for all P in spec R, we can actually compute the stalk of this new M tilde sheaf at P, and it's just canonically isomorphic to the localization of the module M at the prime ideal P in R. So on this side, we see P as a point in the spectrum. On this side, we see P as a prime ideal in the ring. Of course, these two things are the same. And so the nice thing about this M tilde is that even its stalks just give us some commutative algebra information on M. And then also we can know what the sections of this M tilde are on distinguished open subsets. So for this distinguished open subset df, its sections are just the localization of M at F. And setting F equals to 1, as usual, the df is all of x, and the M tilde then just becomes M. And so in principle, the proof is pretty involved, but the good thing is we have already almost done it, because when M is R, this was proven in these two lemmas. It was a longer argument, but then what you can check if you go back to this argument is that if you just replace R by M in the way that we did above, then you can just repeat exactly the same proof. And what is used here is that, well, the only thing that is different in the general setting is that this G, the numerator, is now an element of M. And the only thing that you can't do with this G now is you can't divide by G. This would be nonsensical. But other than this, the only operations that you do, you can still multiply G by elements of R. And this is essentially the only thing that you needed in these proofs. So in other words, so you cannot divide by G, and you also cannot multiply, of course, two elements in the module. And this we also didn't do if you check the proof. And so just exactly the same argument goes through and shows these two things. Because, I mean, kind of the analogous thing that we checked is that the stalk of the structure sheaf at P is the localization of R at P, and the sections of the structure sheaf on df are the localization of R at F. And in particular, the global functions on spec R are exactly given by the ring R. So this is the analogous result. So this gives us a lot of examples now of sheaves on spec R. The question is, does it maybe give us just all of them? Can we get anything like this? And just to conclude this video here, we show that not every O-spec R module is of this form. And to get a certificate that something is not of this form, we actually use this proposition. So for this is also kind of a nice example to keep in mind in your kind of internal library of examples of schemes. If you take the ring R to be the localization of K of X at the prime ideal generated by X, then this, I mean, it's a localization at a prime ideal. So in fact, it's also just the stalk of O of A1 at the point 0. And note here, this thing is not the same as localizing K of X at the element X. If you localize at the element X, then you allow denominators which are powers of X. Here, instead, you allow denominators which are not in this ideal. In a certain sense, that's kind of the complementary way to localize. And so, well, this is the stalk of this scheme A1 at the origin. So this we expect describes A1 at the origin. And if we want to see what is this as a set, it's actually very simple. It just has two elements. Because we know this general result, the prime ideals of the localization are just the prime ideals of the original ring, which do not intersect the set at which we localize. Here we localize at the complement of this ideal. So in other words, we only allow prime ideals in K of X, which are contained in this ideal generated by X. And this is, of course, this ideal itself and the 0 ideal. And these are the only ones. So we just get 2 points. And then you can also work out what the topology is. And in fact, in this picture, we draw all the three open sets of the topology. Namely, you can get the empty set, you can get the full set, and then you can get the set dx, which is the set where x does not vanish, which, I mean, it does vanish here, so it's exactly this complement. And this is everything. So spec R as a topological space is very, very simple. And then we just write down now the O spec R module that we want, and we can just do it by hand because we just need to define what it does on the three open sets and how the restriction works. So so we define this thing on these three sets. We just say on the whole set we want to get 0. This is an R module. Then the interesting part is that on U, which is this dx, you define it basically as a non-trivial module. And so here, before we look at this, let's think about what are the functions on this U. Well, I mean, this is a distinguished open set. So we know the functions are just take this ring here, this ring R, and localize at the element that you want to localize at. So this is X. So we take this ring and then localize at X. Now we have to be careful. Here we localize at this prime ideal, so we're allowed to divide by anything not in this ideal. And so if K is algebraically closed, this just means we're allowed to divide by any function not vanishing at the point 0. And then if we localize additionally at X, well, then we allow to also divide by this function X, X squared, and so on. In other words, we're now also allowed to divide by functions vanishing at the origin. And if you think about it, this just means we're allowed to divide by anything which is not 0. And so, in fact, this localization here is just given by take the original ring Kx and then localize at the ideal 0. And then we just define F to just be exactly this ring, which of course is a module over itself. And then finally, for the empty set, if we want to get a sheaf out of it, we don't have a choice. We just take again the 0 module. So this is the value of this on these 3 points. And then you can check that this is a sheaf. And the reason is just that there are no non-trivial open covers. I mean, the sheaf property says if you have U and you have a cover of this and compatible things on the overlaps, then they glue together. But just, you see, for these three topological, for these three open sets, you cannot cover any of them with stuff that is not already just the set itself. And so for trivial reasons, this F is a sheaf. And now the only claim left is to show it's not of this form M tilde. Well, if it was of this form, F was M tilde, then its global sections, so F on all of X, would have to give M back. This is just this property here. But we defined the global section to be 0, so M would be the 0 module over R. But then we wouldn't get this value at this point, we would just get 0 also here. So these two arguments combined shows it cannot be of this form M tilde. Okay, so not all OX modules are of this form, but many of the very natural ones are. And soon we are going to restrict to only looking at these. And so this is the content of basically this chapter of the course. So we're going to see more about this in next videos.